Hello everyone, welcome to this part 2 of the session on hydroprocessing of digital elevation model and catchment delineation. In part 1, we have seen how we can make use of Saga tools for hydroprocessing of DEM and catchment delineation. In this session, in this part, we will be seeing how GRASS tools can be used for the same purpose. GRASS stands for Geographic Resources Analysis Support System. Both Saga and GRASS are like third-party processing providers or third-party software which can be integrated with QGIS. GRASS tools are considered more robust than Saga tools, as we said, but they may be slow. So let us start with catchment delineation using GRASS tools. In the previous session, we delineated Bhima subbasin of Krishna basin, which is about 70,000 square kilometers using Saga tools. GRASS tools, though robust, they appear to be slow. For that reason, in this session, we will be delineating a smaller sub basin, say Karakwasla Reservoir catchment area. We will be doing. We will repeat the steps of right from the downloading of tiles, then reprojection, then generation of depressionless DEM or filled DEM as it is known in the parlance of GRASS, and then we will generate flow direction and flow accumulation rasters, and instead of deciding upon in case of Saga tools we chose a threshold based upon stream order. Here we will be choosing a threshold on the basis of flow accumulation, and then we will generate streams, and then we will pick up a outlet for generation of or delineation of basin area. So let us start with the download of DEM tile. So we will be using the same source, USGS Earth Explorer, for downloading SRTM 1 arc second or 30-meter resolution DEM. You can use your login credentials by going to this website earthexplorer.usgs.gov, and here you can make use of this option of selecting a address or place in the search criteria, and then you type Pune and click on show, and in the results you will find Pune, which is an the location point location is being shown. You can click on this location to go to the location on the map, or you can scroll to your map and then choose a point or area of interest as we have done earlier. So now I will be looking for the tiles which are intersecting this point and which from the basis of my knowledge about the basin, I will choose a tile or tiles which will cover the whole catchment of Kadakwasla reservoir. You have to necessarily choose a DEM tile or tiles covering the whole basin for doing the catchment delineation. So in the next step you go for data sets, and in the tab of data sets you can choose digital elevation, and there is a separate section on SRTM, and check this box of SRTM 1 arc second global, and then click on results. So here only one tile is intersecting this point because we have chosen our area of interest as a single point. So let us check the footprint of this point. You can change the base map layer. I will get you a topographic map. No, yeah, SRE world imagery. So this tile is big enough, I think, that covers the whole catchment of Kadakwasla reservoir. This is the Kadakwasla dam, and this is the reservoir. So you will have outlet somewhere here on the stream that will be generated, and upstream there are two reservoirs, Varasgaon and Panchet, and then you have water divide somewhere here, dividing the west flowing and east flowing rivers. So this tile, if you is sufficient, or it covers the whole basin or catchment of the Kadakwasla reservoir. So I will download this, which anyway is also part of the 19 tiles that we had provided for delineation of the larger Bhima sub-basin of Krishna basin. Now you can download this GeoTIFF 1 arc second tile. Yeah, once it is downloaded, you can launch your QGIS. Create a new project, and let us save this new project. I will create a new folder with the session name, and here I will name the project. I will also take my DEM tile inside the folder. Now let me add my DEM tile. As you know, it can be added from Open Data Source Manager. Click on Raster tab, choose the layer and add. If you want to see the context, you can go to Web and add a base map, say Google Road. You can change the transparency level of your SRTM layer to see the labels in the base map. Also, you can decrease the opaqueness from 100 to say 50% and then apply. So this is our my point of interest, Kadakwasla Dam, somewhere here, and this will be the part of the basin. Okay. So the first step is there is no need of any creating any mosaic of tiles there, as there is only single tile, and you know the SRTM tiles CRS is GCS, that is EPSG 4326 WGS 84 datum, and you can also see the first layer that we have added, the project CRS is same as that of the first layer that we have added. Now we have to do the reprojection. We need to reproject this tile, because as we will be working with, as we want to calculate the area, and also we will be working with the elevation values which are in meters, it will be more convenient to use UTM projection, and the zone for this, as we had seen in the last session, 43 North UTM zone, for which the EPSG code is 32643. So you can, to do the reprojection, you can go to raster, then projections, then warp reproject. You can also go to the processing toolbox and search for warp, and you will find the tool warp reproject under raster projections under GDAL. So this tool is given a shortcut here under raster projections and warp reproject. Both ways you can launch the tool. Here the input layer will be your SRTM tile, and you have to specify the source CRS and target CRS. The source CRS, you can check it here. You will be seeing GCS EPSG code 4326, which is project CRS. Our default CRS is also the same, but you can go to this globe symbol, select CRS, and then click on predefined CRS and search for 4326 EPSG code. This is the way you normally do when you are going to work with a new system, like there is no memory in your software, QGIS software, and here you can select WGS 84 EPSG 4326 and go back. Similarly, the target CRS, predefined CRS, and you search by the code 32643, which you can find in those websites of spatialreference.org and epsg.io. Now you can select WGS 84 UTM zone 43 north zone, then go back. Yeah, no data value. You can again check the properties of your SRTM layer. Go to information tab and check the no data value defined in the metadata, which is same -32767. You can keep it the no data value as same for the output bands, and then output file resolution in target georeferenced units, that is in meters, it is 30 meters. And finally you can save your output by giving location name. You can go to the this folder and give, maybe you can add grass also, dem field, no, sorry, no, it is not dem field, it is dem reprojected. We are not using grass tool, so you can save it as dem reprojected. Save and run, and once it is done, you will see a layer of dem reprojected added to your layers panel. You can save your project, and you no longer require the original SRTM tile, so you can right click and remove. Till now the steps are common in both GRASS and Saga, making use of GRASS and Saga tools for delineation of basin. In case of Saga tools, if you remember, you had to download one plugin, Saga next gen provider, next generation plugin, and then you had to download the Saga binary files from the Saga GIS portal and unzip the files, and then paste them at a specific location and give the path to that location in the QGIS settings. Alternately, we had also said that you can give path to, in case if you had installed QGIS using network installer, then in the OSGeo for double Windows folder, there will be a subfolder of apps wherein there will be a subfolder of Saga. To that folder, that folder's path can be provided alternately. However, in case of GRASS tools, they are, as you can see under processing toolbox, you will find the GRASS tools are already available, for they are integrated by default, and you can make use of them through by calling them from the processing toolbox. The only setting that you need to do in case of Saga, in case of GRASS tools, is you go to the settings and go to options, and in the left side tab of processing under providers, you will find the grass provider. You can enlarge or open this GP, and then for the first time, if you had installed for the first time, these boxes will be not checked, but you can check them. All these four boxes you can check them, and then click on OK. That is the only setting that you need to do to make use of grass tools. Now, as a first step, we need to fill all the sinks in DEM as part of the hydroprocessing of DEM. We used fill sinks Wang and Liu algorithm in Saga tools. In case of this grass, it has its own algorithm. You can look for r.fill.dir under raster, grass raster. You can double click and check what it does. It filters and generates a depressionless elevation layer and a flow direction layer from a given elevation raster layer. So we will give our DEM reprojected as an input, and it will generate a depressionless DEM, that is DEM field in grass parlance. And also you will get a flow direction layer. It will generate a flow direction layer. So you can give in the DEM reprojected as an input here, and output aspect direction format grass. Grass has its own format of working things. You can keep the rest of the things default, and you can save the depressionless DEM on your file, sorry, onto your system. You can give a name DEM field, say grass, and then flow direction. You need not save it. You can just generate. Flow direction will be useful later as a for flow accumulation. You can just generate it, and then otherwise you can even choose to save it. The name flow direction grass. Click save and then run. It will take some 5 to 6 minutes time, depending upon how big is your basin area, what is the basin that you are envisaging to delineate. If it is a large area, then it will take lot of time. So let it run. Meanwhile, you can check the documentation of Saga, sorry, grass. You can check for r.fill.dir, grass manual. So yeah, these are all the parameters, and then so it takes elevation layer as an input and initially fills all the depressions with the one pass across the layer. Next, flow direction algorithm tries to find the unique direction for each cell. In case of in case of flow direction, it will be in degrees counterclockwise from east in 45-degree increments. So if it is D8 algorithm, we are going for D8 algorithm, then you will find the flow directions like 45, 90, 135, 180, and so on up to 360. So let us, I think it is still running. You can wait and then check till you get the message r.fill.dir is finished. Wait till then. The running of algorithm r.fill.dir is finished. It has taken about 5 minutes 43 seconds. Once you get this message, you can close it. You have one temporary layer of flow direction. No, we have saved it. So you have one layer of flow direction generated, and then DEM field. In case if you are seeing nothing in DEM field, don't worry, it is because of the visualization parameters. You can go to right click and go to symbology, and you can see the render type is paletted or unique values. You can change it to single band gray, as in the case of DEM layer, the original layer and DEM reprojected, and then click on apply. Then you will get the field DEM. So this is the depressionless DEM that you have generated. Now you no longer require this DEM reprojected. You can right click and remove this, and you can look at the flow direction as we had seen in the manual. The flow direction will be having values. You can check using this identify features. It will be having values in multiples of 45, 8 directions, right? And there are some locations where there is no data in case of major reservoirs. So this DEM field, as it will be having a CRS of 32643. Our project CRS is still 4326, that is global coordinate system. You can change it. How to change? You can just click on the right side bottom corner on the coordinate on the project CRS, and then you will be finding the 32643, that is for this region, the UTM zone. Why do we want to change it to 32643? That we had explained in the at the time of reprojection. Now if you want to pick your coordinates, even for outlet, if you want to pick coordinates in this UTM projection, you have to click this and then change the project CRS. You may have noticed a slight tilt of this layer. So you have flow direction as well as DEM field generated. Now we will go to the next step. In case of Saga tools, we had used a threshold on stream order. If you remember, we took the default stream threshold stream order of 5. That means streams of order 1, 2, 3, 4 were not generated, and we have not considered them because we didn't want to generate a very dense network which will not be manageable and which will not serve any purpose. So here also you can you can decide a threshold, but it will be in the terms of number of pixels contributing to the stream. In other words, flow accumulation. You have to decide a threshold of flow accumulation for this for generating the streams. Flow accumulation, if a pixel is part of the stream, it will have a high flow accumulation, whereas the pixels which are on highlines or on the ridge line, they will be having very low flow accumulation. So depending upon your area, the basin that you want to delineate, you can decide upon the flow accumulation threshold. Now before that, we need to generate flow accumulation raster. Now for that, you can go to processing toolbox and look for a tool r.watershed. Under grass raster r.watershed. You can also check its manual. R.watershed calculates hydrological parameters and Rossler factors. This is for soil erosion estimation assessment. So we are not concerned about that, but we will be concerned about flow accumulation raster. So one of the outputs of this tool is the flow accumulation, number of cells that drain through that particular cell. And this is the drainage directions in case of this particular D8 algorithm of grass. These are the directions represented in this manner, anti-clockwise, starting from northeastern. You will also have the option of choosing multiple flow direction, but as it says, R dot watershed offers two methods to calculate surface flow: single flow direction D8 and multiple flow direction. But multiple flow direction, it will distribute the flow to all the neighboring cells rather than only in the direction of the steepest slope by a weighing factor. But if you choose that, it will take lot of time for processing. Even in case of Saga tools, we had chosen T8 algorithm. So anyway, let us come back to the tool. Here the elevation, you have to give it as, the input will be DEM field, and remaining these are all optional: location of real depressions, in case if you have a file of depressions as well as reservoirs, then you can give the input. Overland flow, amount of overland flow per cell, these are not these are of not relevance to us. It will be used for Rosley equation. Yeah, this minimum size of exterior watershed basin, you can give a value of say 500. Maximum length of surface flow, again these are all optional parameters which are not relevant to us. For MFD, we are not using MFD, that is the multiple flow direction. Yeah, you have to enable this single flow direction D8 flow. Otherwise, in case of grass, the default is multiple flow direction. So make sure that you check this box, enable single flow direction, and then you have to save your outputs. The first one is number of cells that drain through each cell. This is your flow accumulation. You can save it by the name flow accumulation underscore grass, and then drainage direction, again this is different from flow direction. Flow direction you have in degrees. In drainage direction, as you had seen in this manual, there are these directions. So you can just generate a temporary layer, or you can save it. Others are not required. You can uncheck all other outputs: slope steepness, slope length, and topographic index, stream power index. These are all different basin catchment parameters. So you check these, you save this as a flow accumulation, and then run. Again, it will give you some warning. You can ignore it and wait for the message: the algorithm r.watershed is finished. Once the algorithm running is finished, you will find this message, and then you can close this window. You will have flow accumulation raster generated, and you can also see some appearance of streams, which are actually the flow accumulation values having high values. Like if you check, if you select this layer flow accumulation, and if you click on identify features, on this black portion, if you check, the value of flow accumulation is about 34,130, whereas in the adjacent cell, which is in yellow, it is just 1. That may be a simple ridge line where the accumulation is only from 1 pixel. So you can check the values are median in case of blue, green, whereas wherever you find the black pixels, they have very high flow accumulation. As you proceed in the direction of the flow accumulation keeps on increasing. See here, the flow accumulation is about 3,10,449. So here it is about 2,29. So you have to make a uh, considered decision on the threshold of flow accumulation for generation of streams in the subsequent step. So we will see that. And yeah, this is the drainage direction. Depending upon the direction, because it will be in the flow can be even in negative direction also. You will be having yeah 1 to 1 to 8, and then even in negative values. Anyway, this is also, we will be using it as an input but not uh, for any other purpose. So you can make use of this as an intermediate layer drainage direction. Flow accumulation we had saved on our system. Now for stream delineation, you have to decide the flow accumulation threshold. Now you can uncheck all these layers and have a look to your, yeah, this is your Kadakwasla dam. Let us change the transparency of this flow accumulation raster to, say, opacity, you make it 50 and then apply. Then you will find the base map labels. Now here you can check the flow accumulation values. The lowest value are in yellow, and then green, blue, light blue, dark blue, and then black, right? So in our case, yeah, you can check the you can select your flow accumulation raster and check the values using identify features. So it appears that the main stream is this one. You can even check the flow accumulation value, which is above 6 lakhs, and the adjacent pixels, as you can see, have very low, and this dark pixels is also low, around 7. This is a tributary which is merging this main river here, somewhere here. Here the flow accumulation is 13,420, and once it merges to into the mainstream, it is around 6 lakhs 5,447. So this is your stream, right? So here you have flow accumulation of about 6 lakh. So you can decide upon a flow accumulation. Like if you don't want all these small streams to be uh, generated as part of your uh, stream network, you can decide upon a flow accumulation of about, say, about 38 or at the most, or you can go for 50,000, as the main stream is about 6 lakh. So now you go for the next step, go to processing toolbox and search for the tool stream extract, r.stream.extract. So it extracts the stream network. You can check the documentation, r.stream extract. So it takes elevation, it takes accumulation, and extracts streams in both raster and vector formats from the required input elevation map and optional input accumulation map. So if accumulation is given, the accumulation values of the provided accumulation map are used. Otherwise, flow accumulation is determined from the elevation map itself. Anyway, we had already generated accumulation map. We will be providing it as an input, and it will generate both raster and vector files of stream segments with unique IDs. So we will be having both raster streams as well as vector channels. So let us run this. So your elevation map will be DEM field, and then accumulation map, you can give the flow accumulation that you had saved. And one more important parameter, rest of the things you can remain. Yeah, minimum flow accumulation for streams. The default value is 1. So you have to change this to, say, we can do trial and error, but we have seen the main stream is about 6 lakhs. You can take anything around 25, 30,000 or 50,000, up to 50,000. You can check and see the stream network. If it is very sparse, then you can decrease the threshold. There is no point in taking a very low threshold. And then remaining things keep as it the default parameters. And what is your output file? The output raster file, it is a line. Yeah, so you can save this unique stream IDs raster. You can enlarge the window. You can save this unique stream IDs raster, that is save to file, stream network raster, which will be in the form of connected pixels, and then unique stream IDs vector. You can, it is analogous to channels that we had generated while using the Saga tools. Stream network vector. As you can see, it is a shapefile. It will be saved as a shapefile. Flow direction optional. You have already generated it. Uncheck this and then run. Make sure that you have provided the threshold value of minimum accumulation and run the algorithm. Yeah, once the algorithm is finished, it will not take much time. It has taken about 1 minute. You can close it. And now you can see that there are 2 layers which are added. One is stream network raster, which you can see pixels. So you can see all other streams are not visible, only the main stream is there because you have taken the threshold of 50,000. And then stream network vector. At the first instance, if it is not visible, don't worry, you can check the attribute table if the attributes are not generated. Check the symbology. Sometimes this vector layer is not properly generated. You can anyway, you have the raster network of channels, but still if you want to run, you can run it again. r.stream.extract with DEM field as your elevation, flow accumulation as an input, and minimum flow accumulation for streams. This time we will not generate the raster streams, we will only generate the output type as line. Let us generate a temporary layer and then we will see. I have ran it for the second time. Now it has generated the layer of unique stream IDs temporary. So what I will do is I will remove this previous layer stream network vector and I will save this temporary layer. I'll right click, export save features as, give the format S3 shapefile, and in the location where you have been saving, you can replace the stream network vector. Click on OK, overwrite the file. So now you have, I will remove the temporary file. Sorry. Now you have the stream network vector as well as raster. If you zoom in, you will find both the files. Now you have to choose your outlet for generation of catchment area. You can zoom to the layer. So this is the channel stream network that has been generated, and you will also find the stream network raster with the flow accumulation threshold of 50,000. You can keep the Google roadmap on for reference, and you can zoom to the extent where you have your there is only one stream. This is the major stream. You have to choose your outlet point by zooming, and then for the tool that we will be using is r.stream.outlet. Yeah, the name is r.water.outlet. Yes. So you can double click this. You can check its water basin creation program. You can check its documentation for better understanding of what are the inputs and what are the outputs. So here r.water.outlet, it creates the watershed basins from the drainage direction map. Okay, so drainage direction will be an input. It generates a watershed basin from a drainage direction map and a set of coordinates representing the outlet point of watershed. So here you have to provide your drainage direction, which you had generated as a temporary layer in the one of the earlier steps. So provide the drainage direction raster. We had saved actually the flow direction, but that was not required. You could have saved the drainage direction raster. And then coordinates of the outlet point in this projection system 32643. Now how do we get the coordinates of this point? You can click on the, once again, you give the drainage direction raster, and then to check the coordinates, you can click on this three dots and your mouse will cursor will change, and then you can zoom to the largest extent possible in that particular pixel, and you click your. Now you see the utility of stream network vector. So vector, it gives you a better reference of where to take your outlet point. So you click somewhere on the exactly on the stream when you zoom it to the largest extent. Then you will find the coordinates are populated in the dialog of r dot water dot outlet points, the coordinates of outlet points, and rest of the things you can generate a temporary file of basin and then you can save it afterwards. So you provide your direction, drainage direction, and then coordinates of the outlet point, and then run. Yeah. So it has generated a layer basin, temporary layer. You can right click and zoom to the layer. As you can see, the Kadakwasla catchment area basin has been generated as a temporary raster layer. And depending upon the stream accumulation threshold that you have, flow accumulation threshold that you have given, you have only the main stream and a minor tributary. If you want to show more streams in your in case if you are generating a map with more and you want to show, because this is a smaller catchment, you can have a flow accumulation can be less than 50,000 for visualization of streams. For generation of drainage basin or catchment area, for delineation of the catchment area, there is no issue. But if you want to show more streams, you can decide upon a lower threshold. So this is your raster. Now you can try to polygonize it and convert it into a vector. For that, you can go to the tool that we had used in the earlier session also. Go to raster and then conversion, then polygonize raster to vector, where your input layer will be basin, which is a temporary layer that we had just generated, and rest of the things you can keep as it is, or you can even save the vectorized file to the file, or you can generate the temporary file and finally save your shapefile and run the tool, and once it is finished you will get the vectorized temporary layer. Now before finalizing and saving the catchment area polygon, you check its attribute table, and you have, as you can see, there are two records. In the previous session also, once we have generated the upslope area and converted into a polygon, we had checked the attribute table, and we said that if there are more than one records, you have to check which one corresponds to the actual basin area or catchment area, and delete the other record which may be pertaining, which may have maybe some geometry issue. There is 1 or 2 pixels which are part of the basin that may have created another record. That for that you can check by selecting the layer, selecting the record, sorry. So you can select the record or the row here and check which one corresponds to your actual basin. Now you see, once you select your um, the row or the record, the second one corresponds to the basin as it is shown in the map canvas area. So you can delete this by going to toggle editing mode, and then the selected feature you can delete. And again, you can check the attribute table. There will be only one record. Yes. And you can come out of the toggle editing mode and save your changes. And now you can save your vector layer, export and save features as, there is only one feature, as Hydroprocessing catchment. Okay. It is still in UTM projection 32643. Now we will try to calculate the area as we had done earlier. Stream network vector, if you want, you can change the symbology and give it blue color just for visualization. This is the main river, and here you will have two tributaries, one another. And then to calculate the area, these temporary layers which were generated, you can remove them. To calculate the area, again you open your attribute table, go to toggle editing mode, and all these fields are also, there will be only one ID field is sufficient. You can even change the value to 1, and then this DN field you can remove it by going to this delete field options and selecting the DN, and you can create a new field and name it as area in square kilometers with the type decimal number. Click on OK, and now you have to update this area using field calculator. Open field calculator option, go to this option, and then update the existing field of area square kilometers. Under geometry you will find this $area function. I'm going fast because we have already done this in the previous session, this function returns the area of the current feature. You double click it and you check the preview, so it gives you the area in square meters. If you want the area to be in square kilometers, you have to divide by 10 power 6. You can look at the preview and then click on apply. OK. So the area in square kilometers is about 543. In the previous saga case, we got 544 square kilometers, about 544 point something. So you can save your changes by coming out of the toggle editing mode and save, and then close. So you had your Hydroprocessing catchment polygon generated. You can do the same, repeat the same process for delineation of any catchment. So here the steps are more or less similar, are same, but the algorithms used are different. Terminology is different. Instead of DEM field, we are talking we are filling sinks. We are talking of filling depressions, and then instead of the threshold of stream order, we had decided upon the threshold of flow accumulation. And the tools used are, we had used 4 tools. In fact, this conversion to raster to vector also, there are tools in GRASS. In the final step, we had converted to vector. For that, we have gone to raster and then conversion polygonize. Similar tools you will find. There are multiple, the same utility you will find tools in raster, in saga, in normal, in QGIS basic tools also you will find. What we had used was QGIS basic tool, whereas you will find one tool under GRASS also for conversion. I think, yeah, R2 vect converts raster into vector. You could have even used this. That's all for this session on catchment delineation using GRASH tools. You can use GRASH tools for delineation of smaller basins without much issue. If you have larger basins, you can look for Saga tools, but Saga tools sometimes it may give you an error because it requires manual installation of and doing the settings. Um, so you have alternate methodologies or tools for the same purpose of catchment delineation. Thank you very much.